This is module number 6 from my online Introduction to Tensors for Non-Mathematicians course or set of videos. It's titled Dual Vectors, and as such, it introduces a special second type of tensor in addition to the first, the primal vector that we already discussed. Whereas the primal vector represents some physical-like value within an n-dimensional space, the dual vector represents some functional relationship that may be applied to a primal vector and generate a scalar output. This exemplifies the idea that tensors can represent concrete values or functional mappings between different values, different primal vectors. If we think of the primal vector as analogous to a column-oriented array, then the dual vector would be analogous to a row-oriented array, and if we take the product of those two, we generate a scalar output. I want to caution you on not taking that analogy too seriously, but it does provide a pretty rough overview of what we're talking about. Specifically, this module formalizes our understanding of this concept of the dual vector, clarifies the notation, and contrasts the dual space to the primal, focusing on the different ways in which primal and dual vectors are added and scaled. As the course title suggests, these videos are aimed at those with interest in science and engineering, with some background in linear algebra, and who ultimately want to learn more about tensors. I have written a text to accompany these lectures, and a link will be provided in the description below when it's available. Still working on that. If you have any questions or corrections, please place them in the comments. I'll try to address them when I can. And as always, please like and subscribe to see more engineering and general STEM educational videos. Let's discuss the dual vector, which resides within the dual space. We're also going to refer to this as the covector. So the dual vector, or the covector, is the second type of tensor that we are going to examine in this online course, this online set of lectures. Previously we had discussed the primal vector. That was the first type of tensor that we examined. Now we're looking at the dual vector. We'll move on to the linear map, as well as the bilinear form, ... moving forward. So we are going to look at several other types of tensors within that umbrella of the general tensor description. Now, the dual vector is different from the primal because whereas the primal the primal vector represented, and I kept on referring to it as a physical-like value, perhaps that qualifier is not needed, but regardless, it represents a value, right? Some value in some n-dimensional space, such as a position, a velocity, could be a charge value, whatever it may be, it's some concrete value. The dual vector is very different in that it represents a mapping. It has a function-like behavior, meaning that it accepts an input, which in this case will be a primal vector, and generates an output, which in this case will be a scalar value. So it represents a mapping between a primal vector in the primal space and some scalar value. And we could represent the mapping as shown here, vector to scalar mapping. Now, in this PowerPoint, in these presentations, we commonly refer to vectors in the primal space, or primal vectors. We're going to refer to those simply as vectors. So if I just say vector, that's implying it's a primal vector. Vectors in the dual space are going to be called covectors. So if I say vector, you'll know that refers to primal vector. If I say covector, you know that refers to dual vector. Now, like a vector, a covector, gamma, is inherently composed of two separate things, and we should be familiar with these terms. It's going to be composed of a basis set as well as some coefficients. Now we call this the dual basis set, and we could call this the dual coefficient or coordinate array. Now I want to talk about this notation right here, because for the primal vectors, what I generally did was refer to the vector as v arrow hat, and then I would say that the primal basis set is b arrow hat, and then the coordinate array is v with no arrow hat. Now one would expect all of these to be bold because they're at least arrays. And we're going to do something similar for the covector. We're going to use gamma, okay, as some representation of the k from covector. I mean, doesn't necessarily make 100% sense, but and we use a left-facing arrow hat to indicate that it's a covector. And this is notation that's specific to, I think, my text and these PowerPoint presentations. I like to, especially in this case where we're talking to an audience that may not be largely mathematicians, I like to try to add identifiers whenever possible. And so what I've done is I've added this left-facing arrow hat to indicate that something is a covector or a dual vector. So we can write it in a similar way. So gamma left-facing arrow hat is equal to gamma no arrow hat times beta with a left-facing arrow hat. So whereas B with the right-facing arrow hat represented the primal basis set, beta with the left-facing arrow hat represents the dual basis set. So you can kind of see I'm using English letters for the primal vector and Greek letters for the dual vector. Now, when we continue on to linear map and beyond, we don't really have any other alphabets to go to, at least not conveniently. So we won't continue that trend. But hopefully you can understand what this means, right? The gamma with the left-facing arrow hat is the covector. Without the left-facing arrow hat represents its coordinate array, and then here we have its basis set. Now, why is the order reversed as opposed to over here we have the basis set then the vector? Over here we have the covector or its associated coordinate array and the dual basis set. Now, the reason why these are reversed we'll see in a second is that this vector right here, the vector array, is a column type, and this gamma will end up being a row-oriented array, and so it only works if we reverse them in this way. Anyway, so to quickly, again, just say the most important part of this, which is that the covector, like the primal vector, is composed of some basis set and some array of coordinates. And then we generate the covector as the weighted sum of those two. Like any tensor or vector, a covector gamma is invariant to change of basis, but its components are not. So we don't really have to say this because if, by transitive nature, if we say that, a tensor is invariant to change of basis, and then we say that a covector is a type of tensor, right? We know that that characteristic should transfer. Now, how do we visualize a covector? I'm not going to spend too much time talking about this because it can be quite complicated to do. I actually want to I've been meaning to do this for several videos. I wanted to refer all of you to a really great YouTube channel called Eigenchris. I'm going to try to put a QR code up here if I can, or maybe I'll put it in the description. They do a really great job of demonstrating how something like a topological map can be used to visualize the covector. So if you're more interested in that topic, refer to the Eigenchris YouTube channel and look for his video on covectors. Overall, I still recommend you check out that channel. He has lots of really great stuff on there. I haven't looked at all of it, but the tensor related stuff I found very interesting. Okay, so let's give our overview, very brief overview of how to visualize a covector. Remember that we visualize primal vectors as a location within an n-dimensional space. And so we talked about this a couple minutes ago for a second, right? The primal vector represents a value. Okay, some value in an n-dimensional space. If we think about it as physical-like, it makes it a little bit easier, something like a position, a velocity, etc. Now, the covector does not represent a value, but a functional relationship or a mapping, right? And we've already seen how that mapping can be represented. It maps from a vector to a scalar value or a real value. Now, obviously, that means we can't visualize the covector in the same way that we represent or that we visualize the primal vector. So to visualize it, we can use something like a topological map, for which we see each point in the space, in the dual space here, is associated with a specific contour or level curve. So what happens is we can imagine some input, right? Some primal vector traveling through this dual space. And these individual lines if we were to think about it like a mountain, represent the height of the mountain. You can see that here. But with regard to a dual space, it represents the magnitude of the individual scales to be applied to it, how much each individual element of the vector is being scaled. Now I'm going to stop there because trying to explain it in more in-depth terms is really going to be quite difficult. So the main difference is, right, the primal vector represents the value. And so we can imagine it or visualize it as some simple, pointed vector arrow in an n-dimensional space. Because the covector does not have this behavior, we need to represent it as some sort of functional, behavior that's applied to a primal vector. And we can represent that using this topological map where different levels represent different scaling values. So returning to the text here, as the vector, and this is what I tried to show here with the point, moves across this map, the covector assigns a scalar value to it based on its position relative to these contours. And so that's going to determine how much it's scaled. The closer the vector aligns with the covector's contours, the higher the scalar value will be, and that's indicated by these contour lines here. And this is similar to the elevation lines on a topographic map. Now, I'm not going to talk more about the visualization again. I really like the way Eigenkrist did it, so I don't want to just try to recreate his work and do a poor job at that. So again, please check out his channel. Now, without visualizing it, I still think we can get a very good understanding of how a dual vector works and what it means to reside within the dual space. So like a vector, we define a covector as the product of a row-oriented coordinate array and dual basis beta, whereas this right here is going to be column-oriented. Right, we have a row-oriented array gamma and a column-oriented basis set beta. Now, we've already said, right, that the right-facing arrowheads indicate primal vectors and the left-facing arrowheads indicate covectors. So here's an example of a vector. You can see that we have, so vector v is equal to its basis set times its coordinate array. The coordinate array is a column-oriented array. And the basis set is row-oriented, but it's really a row-oriented array of columns, right? Now, the covector has a similar format, and I'm sorry if there's too much repetition here. We have the covector is equal to its array, coordinate array, times its basis set. Now, for the covector, the coordinate array is row-oriented, it's horizontal, and the basis set is a column-oriented array, sorry, when I start to write fast it gets very messy, of rows. And so here and here you can see the result of that weighted sum. For the vector, you have the first coefficient times the first basis, second coefficient times the second basis. And for the covector, again, first coefficient times first basis, second coefficient times second basis. So you can see here that the individual bases in the primal space are represented or can be represented by these column-oriented arrays, whereas the individual bases within the dual space can be represented by these row-oriented arrays. All right. Now, the covector may be applied as a function or mapping to a vector, and then as such it will generate a scalar value. So here we have some scalar value z. It's equal to the covector times a vector. Now let's break that down. Over here you can see we expand that. So we have the set of coordinates, right? We also have the set of coordinates. And then we have two different base sets. Now, we're going to assume for a second, and the reason why I have the Ghostbusters stop sign-ish type of, negate symbol on there, is because we're going to assume that both the primal and dual basis sets are standard or orthonormal. And what does that mean? It essentially means that, right, if we're talking about the primal basis set, right, it forms, and I know I went past my boundary right there, sorry, but it forms a identity matrix. So this is what we refer to as a standard set of basis or an orthonormal set of basis, and both of those terms, well, at least orthonormal should be one you are familiar with already. Okay, so, and actually, this would apply as long as one is the inverse of the other, but for now, let's just assume that they're orthonormal. So if the primal and dual basis sets are orthonormal, then the product of beta and B yields an identity matrix. This simplifies the expression as shown below. So here, you see we can represent the output Z as the product of the covector coordinate array and the vector coordinate array. And so this is the type of expression that you're used to seeing in a linear algebra course, where we can generate a scalar as the product of a row and then a column. And in order to upgrade that or represent that as a tensor, all we have to do is consider the neglected basis sets of beta and B. Now, if we multiply the two together, we end up with the summation based form of the expression here, where we're incrementing from k equals 1 to k equals n, and we have the product of gamma sub k and v superscript k. Now again, why is the first k a subscript? Because the gamma coordinate array is row-oriented, and so these are covariant indices. The primal vector is column-oriented, and so these are contravariant or row indices. All right, and so what we can see is if all the bases are standard, then the product reduces to the coordinate arrays only. The covector must apply to a vector with the same dimensionality. And this is the same rule that we see for the product of, a row-oriented and a column-oriented array. So the only difference really between doing that, between multiplying a row-oriented and the column-oriented array in traditional linear algebra and doing that with tensors, is the presence of those basis sets. Now the dual space, so we talked about the primal space before, and so we're going to use a pretty similar definition here. The primal space was that within which all the primal vectors live. The dual space, very similarly, is that within which all the dual vectors or the covectors live. So the dual space associated with a covector refers to that in which the covector resides. It consists of all possible covectors that map the vector inputs from their original primal space to that of a scalar. So all the different covectors that can generate this type of mapping right here. And it should do so while capturing properties like projection or alignment. It also defines certain fundamental characteristics of covectors: the linear functions they represent, their components, their interactions with vectors, and their interactions with one another. And these fundamental characteristics are going to be, at least one part of it is going to be how it reacts to adding covectors together, scaling them, etc. In more formal terms, a dual space is composed of covectors and scalars that may sum and scale in some predictable manner. And that's where we're going to try to do, something like this. So, we understand the rules of that space. So this slide should look familiar. We generated something pretty similar for the primal space. We define the dual or covector space right here. It's composed of a covector set, and that's what this little star up here is indicating. It's a covector set. You could use that simply as notation. You could also take it as indicating some sort of transposition, but I'm just going to use it as a symbol to which math operations may be applied. It's also composed of a set of scalar values. Okay, an array or set of scalar numbers is defined and used to scale these covectors. Okay, this could represent the coordinate array, or it just could represent any set of scalar values that are being applied to it, and that could be part of some sort of a forward or backward transform. We have the covector addition rule, which is going to differ from the primal space or the primal vector addition rule. So the vector space, the dual vector space, this defines how covectors may be added, and then we're also going to look at how they are scaled. So let's compare these addition rules. I think I have a table down here. Okay, great, which will allow us to see the results. So why don't we first look at the table. So we have the addition rule, we have the scaling rule, then we have how it applies to vectors within a primal space and how it applies to covectors in the dual space. So we've already seen this. We know that vectors in the primal space add head to tail, and I put a correction in the comment section or in the description for the video on the primal vector. I don't know why I said that it was the primal vector space satisfied superposition. That doesn't really make much sense given the fact that superposition is generally a characteristic of a function. So I corrected that in the description. So we see that the vectors add head to tail, and we see that the vectors also scale, normally. Now, you can see that the covectors, they do not adhere to the same addition and scaling rules, and this makes sense because the vector, the primal vector, is a value, and the covector is more like a function. Okay, so let's take a look here. So vectors may be added head to tail, creating a single resultant vector. We've seen that already. Covectors, however, may be summed and then applied to an input vector as a single function, or split and applied to each vector individually. So you can see down here that we have, beta A, I forgot to make it left facing, times V plus beta B times V is equal to the sum of those two together times RV. So we can apply them individually, or we can apply them together. And so this is similar to the characteristic of additivity. Then we compare scaling rules. Vectors may be scaled by any real value, increasing or decreasing their length. Covectors may be scaled and then applied to the input vector, or applied to the input vector first, yielding a scalar output that is then scaled. So that's what we have down here. And this again would be similar to the homogeneity characteristic. So what we can do is take a value A and multiply it by our covector BA, and then multiply it by our vector V, and that should give us the same value as if we were to take the value A and multiply it by the scalar value generated by applying B sub A to the vector V. Looking back at these notes, I'm not sure why I used beta to represent the covector. If I was going to do this now, I probably would have used gamma, because generally we reserve beta for the basis, but it's fine for this slide. So just note that unlike most of the other slides and much of the text, we're using beta here to represent a covector and not just the dual basis set. The next module discusses contravariant and covariant transformation rules. What does that mean? Well, we have discussed how forward and backward transforms for covariant change of primal basis may be applied to the components of a vector, both its basis as well as its coefficient array. However, we need to define a similar relationship or a similar set of relationships for other tensor types, one being the dual vector. These rules will help us understand those relationships and how to apply the forward and backward transforms to dual vectors, linear maps, bilinear forms, more complicated tensor types as we move forward. A link to that next lecture is available in the description below or will be available very soon. I look forward to reading your questions and potentially corrections in the comment section.